What do the fiery heart of our sun, ancient dinosaur fossils, and those incredible cutting-edge medical scans all have in common? Well, the answer is a field of science that might sound a little intimidating, but is actually woven into the very fabric of our world: nuclear physics. In this explainer, we're going to unlock the secrets of the atom and see just how much it shapes everything from our history to our future.
And just to understand how high the stakes are, let's start with this. How in the world can doctors see a tumor, alive and active, inside a patient's brain without ever making a single cut? I mean, think about that. The answer isn't magic. It's one of the most powerful applications of the science we're about to dive into. So, here's our game plan. First, we're going to journey deep inside the atom's core. Then, we'll discover how radioactivity acts like nature's own ticking clock. After that, we'll get into the immense power of splitting and fusing atoms. Then we'll see how these ideas are at work all around us. And finally, we'll take a peek at our nuclear future. All right, let's get into it. Section 1, Inside the Atom's Core. To really get a grip on the massive forces that shape our universe, we have to start unbelievably small. I mean, everything really begins right here, deep inside the nucleus of a single atom.
So, what are we really talking about here? At its heart, nuclear physics is all about that tiny, dense center of the atom, the nucleus. It's the study of the protons and neutrons that are crammed in there, and the ridiculously strong forces that somehow hold them all together.
I'm sure we all remember this classic model from science class, right? You've got the nucleus in the middle with its positive protons and neutral neutrons, and then the electrons are zipping around the outside. But for us, for nuclear physics, all the action, all the power, all the potential is packed right there in that tiny core. The atomic and mass numbers, think of them as the atom's unique ID, telling us exactly what we're looking at. Section 2, Nature's ticking clock. Okay, so what happens when that core isn't perfectly stable? Well, some atomic nuclei are just naturally unbalanced, and over time they change all by themselves. But this isn't random chaos. It's actually a super predictable natural process that works like a cosmic clock. And that process, that's what we call radioactivity. It's really just nature's way of finding some balance. An unstable nucleus will spit out a particle or a little burst of energy, what we call radiation, so it can finally settle down into a more stable arrangement. It's one of the most basic ways that things change in the universe. Now, this decay happens in a few main ways. The nucleus can shoot out a little bundle of 2 protons and 2 neutrons. That's an alpha particle. Or it can flip a neutron into a proton and eject an electron, which is a beta particle. Or it can just release a powerful blast of pure energy, a gamma ray. These aren't just random bits flying off. They're signals the atom sends out. Signals we've actually learned how to read and use. So, how do we keep time with this atomic clock? We use a concept called half-life. It's simply the amount of time it takes for exactly half of a pile of radioactive atoms to decay. What's mind-blowing is the range. It can be billions of years for some elements, or just tiny fractions of a second for others. But for any one type of atom, its half-life is one of the most reliable, unchangeable constants in all of nature. And this incredible predictability has some absolutely amazing applications. By measuring how much radioactive carbon-14 is left in a fossil, we can use its half-life to figure out how old it is, even if we're talking millions of years. And in a hospital, a doctor can pick an element with a super short half-life to use as a medical tracer, knowing it'll light up exactly what they need to see and then safely disappear in just a few hours. Section 3, Splitting and fusing atoms. Okay, so natural decay releases energy slowly, but what happens when we want to, force the issue? Well, that brings us to the 2 heavyweights of nuclear energy: fission, which is all about splitting atoms apart, and fusion, the power of squeezing them together. The ideas are basically mirror images. Fission takes a big, heavy nucleus, like uranium, and breaks it into smaller pieces, which releases a bunch of energy. That's what we do inside nuclear power plants. Fusion is the exact opposite. You take 2 really light nuclei, like hydrogen, and you smash them together to make a heavier one. That's what powers the sun and literally every star in the sky. And both of these processes release just incredible amounts of energy. Seriously, think of fission like a cosmic break shot in a game of pool. You've got a single neutron as your cue ball. It slams into a big, shaky uranium-235 nucleus, and boom, it shatters, releasing a ton of energy and, critically, more neutrons. And those neutrons can then go hit other atoms, setting off a chain reaction. Fusion, on the other hand, is a totally different kind of challenge. You have to overcome the natural force that pushes two positive nuclei apart and actually make them combine. To do that, you need absolutely insane temperatures and pressures, the kind of conditions you'd only find in the core of a star. But when they do fuse, a tiny bit of their mass gets converted directly into a tremendous amount of energy. Okay, section 4, the atom at work. We've gone through the basics, the core concepts. Now for the payoff. Let's look at where all this theory actually meets the real world. This is how the physics of the nucleus is shaping our lives every single day, in hospitals, on farms, and in our power grids. And this brings us right back to that question from the beginning. Nuclear physics is kinda the silent hero of modern medicine. PET scans use the predictable decay of those radioactive tracers to make cancer cells literally light up on a doctor's screen. And MRIs? They use the magnetic properties of the nuclei in your own body to create these stunningly detailed pictures, all without any harmful radiation. The way a PET scan works is just brilliant. Doctors attach a harmless radioactive atom to a sugar molecule. Now, cancer cells are super greedy for energy, so they gobble up this sugar way faster than healthy cells do. As that radioactive atom decays inside the tumor, it sends out a clear signal, a pair of gamma rays flying in opposite directions, that a scanner can detect, letting it pinpoint the cancer's exact location. It's amazing. But it doesn't stop at the hospital. Nuclear physics is also hard at work on the farm, which might surprise you. It helps scientists create new types of crops that are tougher and more productive. It can control pest populations without harsh chemicals by sterilizing insects, and it even lets farmers get super precise measurements of the nutrients and water in their soil. And of course, there's the big one, generating power. Nuclear fission isn't some sci-fi dream. It's a huge player on the world stage right now. By controlling that chain reaction we talked about, nuclear power plants generate about 10% of all the electricity on the planet. That's a massive piece of the pie. And beyond our day-to-day lives, nuclear physics is how we tackle the biggest questions imaginable. It's how we piece together what happened in the first few moments after the Big Bang. It's how we hunt for brand new particles at places like the Large Hadron Collider. And it's how we understand the stellar fusion that creates the very light and warmth that we depend on to survive. Section 5, our nuclear future. All right, we've gone from the tiniest particles imaginable all the way to the heart of stars. So let's pull back, look at the big picture, and ask the big question. Where is all of this headed? When you really step back and look at everything, the conclusion is pretty clear. Nuclear physics isn't just some abstract thing you study in a classroom. It is a vital, powerful tool that we use every day to heal people, to power our cities, to feed the world, and to understand the universe itself. It's a fundamental and often invisible pillar of our modern world. Which leaves us with one last really crucial question to think about. We've figured out how to unlock one of the most fundamental forces in the entire universe. We've used it to heal and to build our civilization. So the only question left is, with this incredible power right at our fingertips, what's the next great challenge we're going to solve with it?